Hello guys, my name is Shivam Pandey and you are watching me on this for an Uncode YouTube channel. This is our fourth lecture on the topic trees and this is a very important lecture in terms of your weightage inequity. The topic we are covering today is BST traversal and we would also see the code of BST traversal like pre-order, in-order and post-order traversals. Also, we would be covering up some questions which you would be able to solve the traversing and the insertion deletion questions of the binary tree. Also, you will be getting the operations of the binary tree, and yeah, so different concepts are there in today's lecture. So let us start by the very first question we have here. Yeah, this is a tree which has the root node as 100 and the parent node of the root node are 20 and 200. So 20 has also two children of 10 and 30 and 200 is also two children, which is 150 and 300. So if we see upon the pre-order traversal of this tree, then we see that 100 is the root node. So it would be at the first place, correct? So 100 is at the first place, so it is correct. And after that, we have to look upon the left part of the root node. So the left part of the root node is here, which is 20, 10, and 30. So we have to again look upon that out of 20, 10, and 30, which is the root node or which is the parent node. So it is exactly, or it is very easy to find out that 20 is the parent node here. Yeah. So we write 20 as the parent node, and then we have to find the left and right child of this 20 parent node. So the left child is 10, and the right child is 30. Yeah. If we arrange this into an order, then we get 100, 20, and 10. If we look upon the right subtree, then 200 is the parent node, and 150 and 300 are the children of this parent node. For 200, the left child is 150 and the right child is 300. So if we arrange it in a particular sequence, then we get 150, 20, 30, 30, and 200, 150, and 300. So it is the correct sequence that we will be getting in this manner for pre-order traversal. Now for in-order traversal, we have to keep the parent node in middle of the children. So for in order, we have 100 in the middle of the whole these two subtrees, and for this part of the subtree, like 20, 10, and 30, 20 will be in the middle, and 10 and 30 will be the at the like adjacent to this 20. If we arrange this into a particular sequence, then we get 10, 20, 30, 100 in the middle of both the subtrees, and 150, 200, and 300. This is the like correct order for the inner traversal. For post order, we have to arrange the root node at the last place, so that the parent node or the root node comes to the last place in the post order traversal. As the name only suggests that it is in the post-order traversal. This means that the elements are the parent elements are present at the last, and the left child and the right child are in the beginning. So here you can see that 10 and 30 are in the beginning, and 20 is at the last place. Here also 150, 30 in the 300 in the beginning, and 200 is the last place, and the root node 100 is at the almost the last place that would end the traversal. Correct. So if we look upon the code, the C code, which by which we can implement these traversals are like this. So we have made a function which is named as void in order here, and in this in order, you have to pass one parameter which is node, and which basically denotes the element or the address. Sorry, it won't be address, but it would be the root which or the node which you want to insert in the tree. For example, if you write here if you in the main function, if you write here in order and in bracket you pass the parameter as root, then and slash, then arrow, and you write here right. So it will move the element in the rightmost part of the selected parent child. Yeah. So in order, if we pass here like a root and then slash, then arrow left, then the parent child would shift the element into its left child, and the element would be inserted at the left part of the parent child. Yeah. So this was the code. This is very easy. We have taken one if statement, and if in this if we have passed the parameter that root is not equal to null. So it basically means that if the root is equal to null, which means that no other element is present in the tree, then it means that the array is ended and it has no other element. So we have to look upon this, and this if statement is checked every time the element is being inserted into the tree, and it checks this multiple times. But in the case if the root remains null, then no other element will be inserted into the this tree. Yeah. So yeah, for just do one thing. If you get the in order, then basically write the root data in the middle, and if you get first order, then write the root data in the last, and if you get pre-order, then write the root data into the first. So this is the basic difference that you get, and all the other statements like root null and no root would be same in all the three cases. You have got one example or a question, you can easily solve it, and there is nothing to teach you in this. But if you want, then I can solve it also. There is no, this is not an issue, and yeah, so we can solve it. So let us see one example here, or leave it. I will just make another video where I will solve all the questions and all the queries related to this topic, and I will take these questions there only. Okay. So here we will only cover the concepts, and the numerical and the question part will be taken up there. Correct. So let us see upon the base tree operation or the binary search tree operations, which we would be getting, and this is the part from where you will get your questions in your exams. So the questions which are given into your exams are like search operations, insertion operation, deletion operations. Yeah. So if you get a 7 mark question, then the first part asks you to make an tree, and the second part asks you to search for an element, and the third part basically asks you to delete an element from the tree. Yeah, so if a questions come, then it would combine these parts, and then a question would be made for you. Yeah, so for searching is basically very much easy, and it is not that much tough than insertion and deletion. But you have to keep in mind that if a parent node is there like this 25, so the element which is greater than 25, or which has a value which is greater than 25, or this year says 26, 50, 100, or any other value, would be placed at the right place of the as the rightmost place of the parent node, and a value which is less than 25, which is 24, 23, 20, 15, anything, would be placed at the left part of the like the parent node. Yeah, so if I see here, for example, let us not take the situation which is given in the question. Let us do something by our own and learn something new. So if we try to search 70 here, yeah, we don't know that where 70 is actually in the tree, but we have to find it by ourselves. So we go upon 25, and we think and compare here 70 and 25. We think that 70 is greater than 25. So we should the thing which comes into our mind is that we have to move towards the right part of the 25. Yeah.
So we move toward the right part, so we come upon to 50. Yeah, so 50 is also, if we compare with 70, then 50, then 70 is greater than also 50, and 50 is less than 70. Yeah, so the image is clear. We have to again move towards the right of the 50 to get a number which is greater than 50. So if we come upon here, then we see 70. Yeah, so here we get our value 70, and if we have to find out, let's say 66, then we think, then we get a thought in our mind that 66 is less than 70. So we have to move also, so we have to move towards the left of the parent node 70, and we would get our value there. So yeah, if we come upon the left side, then we are getting our value 66 over here, and it is the required key which we wanted. Yeah, for insertion. Now let us find out, let us read this point and see what is written over here. So the insertion of a new key always takes place as a child of some leaf node. For finding out the suitable leaf node, search the key to be inserted from the root node till some leaf node is reached. Once a leaf node is reached, insert the key as child of that leaf node. Yeah, so the basic concept behind behind all these three concepts are that you have to always keep in mind that you have to move towards the left if the value of the node you are entering is less than that of the parent node, and you have to move right when the value is greater. Yeah, so you have to insert 40. So compare 40 with 100, it is less than 100, so you come towards the left. Then you see 20, so 40 is greater than 20, so you come towards the right. Then you see 30, so you see that 30 is vacant and no child is there of 40. So you do one thing, that you insert 40 at the right place of the, or the right node of the 30. So 30 becomes the parent node and 40 comes into the right part of the parent node 30. So that was the insertion. And similarly you can insert the elements at different places depending upon where you want to insert them. So now let us see the deletion operation of the binary search tree. So deletion operation is performed to delete a particular element from the binary search tree. When it comes to deleting a node from the binary search tree, three cases are possible. Yeah. So now let us see one by one that what are the cases that we can have while deleting a node from a BST. Yeah. So case one is that deletion of a node having no child. Right. So now let us see what is the concept behind it. Just remove disconnected leaf that is separated from the tree. Yeah, so if we want to read 20, then there is not much big deal in it. You have to go towards 20 and you have to just delete the this element or the node from the tree without any second thought. And if you delete, then you will get your desired tree after the deletion. Yeah, so we have deleted this 20, and the updated or the tree after the deletion is this one. Yeah, so this is the thing. Now come towards case 2, deletion of a node having only one child. Yeah, so if, let's say, if we have an element or a node 30, so 30 is having one child at the right part 40 also. So we can't simply delete this 30 and we write 50 only, and then we start this rightmost part. There is also 40 to the right part of the 30, and we have to take care of it also, because we can't simply leave this whole part of 30 and we can't ignore it, right? So for processing this, we have to do one thing, that we have to delete for 30, right? So we delete 30. Yeah, and we see that is there that if there is any like any child of 30, for example in this case it is 40. So we do one thing, that we push 40 above its level, and we put 40 in place of 30. So if we put 40 in place of 30, then we get 50 as the root node and 40 at the as a left child of the this BST, correct? So here you can see the updated or the corrected version after deleting the value 30. Now here it comes the deletion of a node having two children. So it is the point which basically you have to keep in mind every time you do deletion of node in BST. Yeah, so it has two methods. Like if, for example, if you are having a node which is having two children, yeah, so then what are the things we are going to do? So you have to not just worry about the thing. For example, if you have to delete this 15, I don't know how. Yeah, so the question also says that that you have to delete 15. So you do one thing, you delete 15, and either you go towards the left child, and then from the left child you have to come towards the right child of the left child of the root node. This is the method one. But if you don't want to follow this, or you don't get an option to follow this, then you do one thing. Then you come towards the right part of the parent node, and then you come towards the left child of that parent node. Basically you have to like make this type of thing, that this you have to come towards the left and then towards the right. You have to come towards the right, then towards the consecutive left. So this is the path you have to follow. And then if you follow this path, then the element on which you will reach after this, then you have to place this 16 in place of 15, or you can either place 12 in place of 15. You can do both these things. You can see here also, yeah, so they are placed 12 in place of 15. Yeah, so you can either do the method 1 or method 2, both are correct, and nothing is wrong in choosing one of those methods. But in my opinion, just analyze the BST and see where the elements won't get disturbed if you like delete the element. For example, if system is also having some nodes here, like some like some root nodes here, then you do not change the configuration of this 16. You choose the easier path, and you change the place of 12 and you place 12 in place of 15. Yeah, so in that case it would be easier to do such things. But if you easily can delete any then if both the roots are clear and no children are found on both the roots, then you can easily delete any one of them. And that's the very normal case, and no complexity is required over there, so you can do these things easily. Now we are having a concept of hashing. I guess hashing is an individual and a long topic as well, so a dedicated video is required for it. And if I continue hashing today, then it would be long. Then the video would become very long. So I recommend that I should teach you hashing in the next part of this tree series. Yeah, so for today the lecture is over. So thank you for joining this lecture, and let's meet tomorrow again.